All right, are you all Desmosed up? This is Desmos. If you haven't downloaded this, you should do it. And just put in the function x sine 1 over x. You don't have to do the rest of the stuff, but this is a really good thing to just start exploring with. All right, so there it is. It doesn't look much like what we graphed. It's like a very boring graph, but then it's got this little squiggle in the middle. It's all about the little squiggle. Look at that crazy squiggle. So if we get to here, this is 0.2, 0.2, 0.2, 0.2. So this is sort of the same window that we saw with TI. And you can see it's a lot more smoothness in this graph. So here's our first epsilon band that we did. Come on, turn on. Right, so this is epsilon equals 0.1. So our epsilon band is 0.1 here. And we determined the delta band for that was, I think, negative 0.119. Here I put 0.1187. I calculated the intersection. So that means that as long as we're between that delta band, as long as the x is between the delta band, all of the function values lie in the epsilon band. All right, so that's a start. But the calculus process is you make that band smaller and smaller. So now we're going to go to an epsilon band of 0.5. So if I can scroll up here, there's the epsilon band of 0.5. Come on, turn on. Here you go. So here's 0.5 up here and negative 0.5 down there. So it looks like in order to, like at this time I've got a protrusion down here. So if I want all of the y values to fall within the epsilon band, I'm going to have to exclude this bump and put my delta band like that. So here's my delta band, jabing, jabing. I picked negative 0.5632, and you can see that that causes all of the function values to fall within both the epsilon and the delta bands. But of course, for calculus, what we want to do is get things smaller and smaller. So I got crazy and I went down to epsilon equals 0.01. Yeah. All right, so we can scroll up. 0.01. There's the epsilon band at 0.01. Where's the delta band going to be? Well, I'm going to close it here. And you can sort of see, by the way, what delta band is going to work generally. See how when I have y equals when I have the epsilon is 0.1, really this is epsilon and this is delta. Well, delta is the positive one. So I have epsilon is 0.01, delta is 0.0101. So I can always use a smaller delta. And if I use a smaller delta, I'm going to have even more of the points be inside. So smaller delta is better. So what I've been seeing is a delta that's slightly larger than the epsilon. So in general, the delta that's always going to work for this is just delta equals epsilon. So for every epsilon, there is a delta, namely delta equals epsilon, so that if the f of x values are within the epsilon band, then the x values are within the delta band. And that's it. So like if you kind of get that idea that that's how the epsilon and delta band works. The epsilon and delta band are just boxing in the function at tighter and tighter levels, and they can keep doing that forever because epsilon and delta are both positive numbers. So I guess at this point I can't really graph it anymore. Let's see if we can. Yeah, I can't do it. But and you can see how delta equals epsilon, because this is like the y equals x and y equals negative x line. So delta equals epsilon will constrain that and make that work. All right, so there you go. That's a little bit about this function, one of my favorite functions. I was just noticing that this is all about, for every epsilon you can find a delta, right? And I sort of forgot to do that part for a previous function. So we'll throw that in here. We determined that for this function that we started with, x over cube root of x, the delta that's always going to work is square root of epsilon cubed. So in this sentence, what you want to say, and you do want to write it over, I'm going to cheat and just fill in the blanks. It's about this. For every real number greater than 0, there exists a real number delta, namely the square root of epsilon cubed, or we could say delta equals the square root of epsilon cubed, so that if absolute value x minus 0 is less than delta, then absolute value of f of x minus L is less than epsilon. In other words, if the x's are close enough to c, then the f of x's are close enough to L. Therefore, the limit as x approaches 0 of f of x equals, what was it, x over cube root of x? Or was it the other way around? X over cube root of x. X over cube root x is 0. So that's how we're filling this in. And what it's always about is, for every epsilon, I should be able to find a delta. In any epsilon, I can cube it and take the square root and get delta. If you go way back to limits number 1, somewhere we were doing a function where we determined what, actually it was limits number 2, I guess. Yeah. And we found that, I'm going to regret doing this. Oh yeah, that any epsilon, so for any epsilon, you can divide that epsilon by 1.17, take the square root of it, and get a delta. Therefore, for any epsilon greater than 0, there exists a delta such that if we are within delta of the c, if the x's are within delta of c, then the f of x's are within epsilon of L. And that delta, namely, is square root epsilon over 1.17 for this function that we did in limits number 2. For this function, that delta is somewhere, square root epsilon cubed. For this function, we can just use delta equals epsilon because essentially this function is like coming in like this, and it's always constrained by the lines y equals x and y equals negative x. It's always sort of be stuck in there. And so if I just choose delta equal to epsilon, they're just all going to fit in there. So we could see that with some of the numbers. All right, so that is my favorite function, x sine 1 over x. Oh, I took that picture. That's my flower. That's my hibiscus. All right. Yeah. It's an awesome function. So, oh, by the way, what's right in the middle? A hole. Boom. Zoom way out. Right? It's cool stuff. It's a cool function. Now, all our epsilon and delta bands are in there. Because epsilon and delta bands, we think of them as being small. They don't have to be. It's any epsilon greater than 0. But the ones that matter are the small ones. All right. Next up, we're going to look at this function. Wait. We're going to look at this function, sine x over x, which is extremely important. We're going to get an extremely important result from that.